Hello everyone and welcome to MLAS100, Learning Activity 2, Computational Learning Theory, and we are going to be jumping into it now. So now that we've got our lecture 0 kind of out of the way, we've gone through up to this point course structure, run through the syllabus and talked about things like that, and then Learning Activity 1 where we went through the history of AI, and you gave me some time to talk through what that looks like from cultural perspectives of AI, historical perspectives of AI, and kind of what the implications look like for artificial intelligence as it relates to cybernetic systems theory and autonomous systems and what we're doing here. We're now going to be jumping into the meat of the course now, in terms of this is where we're going to start to jump into computational learning theory. So let's start by talking about what, if I can get this, there we go. Man, it's a little slow. So when we talk about computational learning theory, sometimes it's just called learning theory. It's a subfield of artificial intelligence and intelligent systems. So computational learning theory has a lot of different, we're going to talk about the main big buckets, which is going to be unsupervised learning, supervised learning, reinforcement learning, and a little bit on deep learning here. And of course, and there are a lot more. So I want you to refer back to your handbook, your MLAS handbook, and just do a quick read. It's not a lot, but just do a quick read on unsupervised learning, supervised learning, reinforcement learning, and deep learning. And then you'll notice that there are a lot of other learning methods. These are what are called the core learning methods. There are others like zero-shot learning or one-shot learning or ensemble learning methods. There's just a lot of different types of learning methods, but these are the core. So let's talk about these, which is unsupervised. So unsupervised is when we take input data and we use statistical or math models, they're pure math models, to see if we can make sense or create a pattern off of the input data. And it may seem random going in on the input, but when we apply a mathematical model, we can actually cluster the data. And typically we have different capabilities or different ways we can cluster the data. We have different algorithms, and we call these unsupervised clustering algorithms. But usually what we do is we have in this as one example of many, because there are many different unsupervised learning algorithms. Is you use a statistical model or a calculus-based model or a linear algebra model to create a an analysis of the input data that organizes it in such a way that, in this case, it creates clusters or groupings of the data. Humans are really good at doing this. We could actually do this really quickly on the left-hand side. Computers can do it very quickly too, but it takes a lot of heavy lifting for computers to do this. Now, with that said though, computers have gotten so much more advanced. So our ability to analyze and cluster data, we have created way more data than we could ever hope to classify or cluster, rather, in this case. Then we've created our ability to analyze data is way behind the amount of data we've created. But this is an example of unsupervised learning. But let's talk about what this looks like in the data itself. So let's say we took a string of letters. So in this case, I've got a data string which has XOB or BOX boxes. So it's just letters of B, O, and X in a string. Well, I can actually break that string up, and in this case I have 77. I have an n sample. We use that by denoting little n versus uppercase N, which would be a population sample. In this case, this is just a sample of the population. So it's this little n. So it's 77, and we've found a pattern. So you can see here on the right hand side, we've got a pattern of what that looks like. Now the question is, what's the pattern? And then we can do a simple count. We can say how many, there's nothing crazy about it. We just say, well, count the instances, and that could be the algorithm. So you could create, in pseudocode, right? We could say this out loud. In pseudocode, we could say, what are the number of distinct patterns in the string of letters, right? And so in this case, we'd say the pattern, we'd find that B equals to 24. If we counted all of them, we'd say B equals to 24, O equals to 34, X equals to 19. But we can also see that there's kind of this clustering pattern that happens towards the single N, and that's something we can only visually spot. You can kind of see this clustering that's happening in the tail, where we've got this XXXXX and then OOOOO and so on and so forth for B. Now, that is an example of unsupervised learning at the highest of highest levels. There's actually, when we just talked around pseudocode for the algorithm that we had just come up with, that's the basics of basics, right? But it is still pertinent from an unsupervised learning method. We created a simple algorithm, and then we broke it up based on the counts, the patterns. We just did it based on number of counts based on distinctness of a given letter in a string. Now, if we go on to supervised learning, it gets a little bit more complex. So in supervised learning, we have a two-step process. One, we have our input data, creates a model. In this case, it separates the model. Then that goes to another model that asks another question. So forecast what grows best next season. In this case, I'm making this up. I'm just saying that peaches are going to grow best next season. But that is the essence of supervised learning. It's a process where you take the input data, we break it out into it could be these clusters as inputs or labeled data inputs, we say. And these labeled data inputs would then be put into another model, which then goes and asks the question. It's a predictive question. What happens next? So there's a big distinction here. In the unsupervised learning world, it's not about prediction. It's just about describing the patterns in the data. That's it. Describe to me that I have apples, peaches, and bananas, and that's just what we call a current state of the data. Tell me what it is telling me. It's descriptive. Now, in supervised learning, it's that plus predictive. And this is not always the case, because we can use supervised learning for what's called classification. But I do want to make, I don't want to muddle that up right now. So I'm just trying to keep this simple. So supervised learning is where we take this and we create a forecast. Now, when we get into more advanced topics, we'll teach you that supervised learning can be used for classification and prediction, but that gets into us having to describe the distinction between clustering and classification. I will help you with that. So just to keep in mind, for right now, I just want you to kind of be of the mindset that in unsupervised learning, it's about this is the two things. Unsupervised learning, I want you to have an understanding that it's used for describing the current state of the data. In supervised learning, for now, supervised learning is about describing what happens next in the data. So those are the two big highlights, and we'll talk about more complicated things down the road. So more different distinctions of that. Okay, so now let's take supervised learning part 2 and break this up. So now what we're doing, back to what I was describing, supervised learning for what happens next. Well, how does an algorithm describe what happens next? So in this case, we have our same string, but what I'm going to ask is what happens over the next n sequences. So if I take this and I say, okay, now if I was going to predict what happens next, how do I forecast that? And this is the very essence of machine learning. So in this case, I'm still using the same string, but what I'm going to use is what's called a moving average. It's a very simple algorithm, and it's something that everyone here knows right off the bat. But it's a little different. It's the average. Calculating the average, I think we all understand. But how do I calculate a moving average? Well, I will show you. Now, the next thing I have to show you is, well, how does the machine understand BOX? Well, what we do is we vectorize the categorical data. In other words, we take the data and assign a numerical value to it so that the machine understands what we're asking, right? So that it can calculate what it is that we're trying to do. So in this case, I'm going to assign 3 to be O to X1. So then those are the 3 categorical numbers associated with those categorical data points that are textual. And what I do is I can actually create a forecast now, and after I've vectorized that and applied a moving average algorithm, I can then create a forecast off of that. So then we can say what is going to happen next in the next n sequences. Well, I can predict that there's going to be O for the next 7 and B for the next 3 after that. How did I do that? Well, there is a way we did that. So now let's talk through this high level, simple supervised learning. So everything on the left is training data, everything on the right. So this is a series of that string. This is a partial. If you come up here, this isn't everything on this list. This is just a snippet of that. Otherwise, it'd be hard to display it. So I'm taking just a little snippet of it. But a moving average is, so for example, I'm taking these spots and there's a frame. So you have to identify the frame for the moving average. In this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So my moving average is, I'm taking the 17, that's my frame of reference, and then I'm going to create a average of that and then plot that out next. So I say take an average of that and then move it forward to 2.0, and then what is the value? 2.06. Well, 2.06 is closer to 2, which means that I assign it a value of O. So that's the threshold I'm going to use. And then I shift my frame of 17 over 1 to include 2.06, but then drop the last one. So in other words, I'm moving it every 17 frames. I keep moving it forward. So in this case, my moving average is taking a sample of 17 and comparing training data and then creating a predicted forward-looking forecast of that data. So then when I move that average forward, in the next step, I get 2.19. If I move it again, then I get 2.27. And then this is how I get this O predicted. So 2.48, that's the last time I see O as a value because it's under 2.5. So I'm using a rounding method that, and for me, for my moving average algorithm, I'm going to say when it crosses over 2.5, then it crosses over into an X value. So that's kind of the way that you have to have some kind of threshold that you apply to it in this case. But this is a very, very simple, basic supervised learning algorithm. And it's actually one that has a lot of usage when you looked at in market analysis and investment analysis and ticker stocks. Moving averages are algorithms that are used to help forecast the movement of a price in a very short period of time. So this is one of hundreds of supervised learning algorithms. There's just hundreds, if not thousands, of supervised learning algorithms out there. But this is a way to help visualize at a base core what a supervised learning algorithm looks like. Okay, next up, reinforcement learning. So in this case, reinforcement learning is a little different than it's in the sense that I have a reward system that is imbued within the data set. So in this case, I've got so we can still use the same data that we've been working with, but reinforcement learning, it's that middle word here, this rewards that is very, very important when it comes to reinforcement learning. So reinforcement learning, again, using the same data set that we've been working with, this data string, right? Now what I'm going to do, and I'm going to use the same algorithm, but I'm going to have a moving average with reinforcement. So I do all the same things. I have a moving average, I vectorize the categorical data, then I positively reinforce the occurrence of X. In this case, I'm making this up. That's what I want to do. And then in the case of I see the occurrence of B, sorry, not C, but B, I'm going to negatively reinforce the occurrence of B. So let me just change this right now. That should be B. Not sure why that says. Let's say B. There we go. Get back to this. That way, because I'm going to share these slides out with everyone. Everyone will have a copy of these. I'll get these uploaded today. So, negative reinforcement, in the occurrence of a B, you subtract 1. Okay. So then we ask our question, what is going to happen over the next XYZ, right, over these next spaces in the sequence? And then it actually turns out it's going to be X for the next 10. So when we add a reinforcement mechanism into this, in this case, we reinforce positively the occurrence of X and negatively reinforce the occurrence of B. It turns out we actually really changed. It went from going the opposite, one direction, going up to B's, to our reinforcement mechanism made the next 10 be X. Totally off of the line, right? Very, very different. Strongly X, as a matter of fact. So we really negatively reinforce the curve. Okay, now, how does that happen? So it happens by us adding a reinforcement vector. So in this case, what I did was, again, same movement, right? I have average, and then it's moving, ignore this Z that's over here. But I've got the same moving average. And then, but over that same time frame, what I've done is, remember I said anytime I have the occurrence of X, I positively reinforce it with a 1. And then anytime I have a B, I negatively reinforce that 3 with a -1. And then what I do is I average both vectors. I average this vector right here, and then I include the positive ones and the negative ones in the vector as well. And so when I shift that average over, the first one, it becomes 1.21. I shift it over, it becomes 1.23. I shift it over, it becomes 1.25. It actually goes all the way up to 1.32, but then it starts coming back down. And then that actually should be X's all the way across here. So I've got 2 mistakes. So these should be all X's. What we're showing here in the prediction. So 1.21 to 1.12, these are all X's right here. This is just an old graph that I was adjusting. So anyway, that's something to keep in mind. That's something that I actually will have fixed in the slides when you go take a look at it and download that. I'll have that fixed so it shows all X's. So in other words, what you see on this graph should be all X's as they approximate 1. Okay, so that's how that's done. So these that's reinforcement learning, and next up is deep learning. Now, deep learning uses what's called neural networks, and so in this case, you can see on the bottom, I can use a neural network for machine learning. And I think the biggest difference between machine learning and deep learning is that deep learning isn't like going more comprehensive learning, isn't like that, or going deeper into learning. It isn't like that. Deep learning is about taking a neural network and then adding, and it's always a neural network of some kind, whether it's a convolutional neural net, whether it's a deconvolutional neural net, whether it's a recurrent neural network, whether it's a generative adversarial network, whatever kind of neural network. Maybe it could be an ensemble neural network of multiple neural networks. It's that, in other words, it's a deep, that is what describes deep learning, is all these little hidden layers. This one has one, two, three. This one has three hidden layers, or I guess technically it, depending on what's on the left hand side, but just based on what's being described here, I've got three hidden layers, and in the upper one I have two hidden layers for machine learning. And that's the main distinguishing characteristic between deep learning, is one, it uses neural networks, and two, it uses a lot of hidden layers. And we'll get into this as you get further along into the programming side of the courses. We'll get deep into a lot of the deep learning as well. Even though we have a supervised, unsupervised, and reinforcement class, we're actually leaving deep learning up. We'll cover deep learning within those classes. Specifically, you'll start to see that show up in sprinkled throughout the courses. So deep learning is one of those things we'll pick up as we move along as well in your coursework. Okay, so oops. Let me get back to here. All right, so the one thing to keep in mind is there is going to be I'm just double checking on a date here. All right, so our first quiz is going to be 9-4. Just update this. There we go. And so that's something to be on the lookout for. And that's you don't have to worry about that this week. Just focus on the lectures, focus on this. Later in the week, towards Sunday, I'll have another set of lectures that I'm going to post for week 2. And then be on the lookout for our, I'm going to open up the quiz next week, not this week, but next week. And then I'll have that open for everyone to take. Probably Wednesday next week is when I'll have 9-4, that quiz opened up. It's due on 9-4, but that's a suggested due date. That's what you want to shoot for in getting your quiz done, but I will leave it open in case something happens, you have a conflict. So if it turns into 9-5, you need to take the quiz, that's okay, even if it's 9-6. I would suggest not to go too much farther than probably 9-6 or 9-7 in taking that quiz. But that's a suggested due date. So make sure you hit that, and then you'll be good, because then you'll be fresh to jump into week 3 and week 4 activities where we start to ramp up on the material. So it starts to get a little bit harder. Okay, that's all I have for this week. Nothing crazy to run through. Some things you want to just keep on top of is make sure you've watched all these lectures. Make sure that you've read the machine learning, the MLAS handbook, and the topics related to this. And then I, of course, will have these uploaded, and you'll be able to access these later today. Okay, that's all I have. That covers week 1 materials, and I will see you in week 2.